Hi, and welcome to today's lesson on solving exponential and logarithmic equations. It's really a continuation of what we started the previous day, which focused mainly on just solving logarithmic equations. Now we're going to actually look at a mixture of exponentials and logarithms. To start, we're going to actually consider a problem that was posed a few days ago and actually worked out in one of the previous video lessons. A good intro and a good reminder of some things to be aware of for this lesson. So we were considering before an equation like 7 to the power of x equaling 400. The issue with that equation we determined before was that unfortunately 400 is not a power of 7. So we would be unable to sort of treat this exponential like others we've dealt with in the past where a common base was possible. One thing we would need to be aware of is there's no integer value of x as far as one thing we need to be aware of is there's no integer value of x that if I raise 7 to that power I get 400. So we would be anticipating likely a decimal answer in this case. Right? Now because there's no common base possible, a different approach would need to be used. What we would have determined before is that actually taking the common logarithm, so the base 10 log would make sense to use here, although the natural logarithm would also work. Either or would be a good choice. And the one thing we can exploit here that relates to logarithms is actually the power law. So what we would have seen before, basically our first step would have been to take the logarithm of both sides, and now on the left side we can see, well, the power law could be used to remove the x from the argument within the logarithm. So then that would bring us to our next step, which is to, again, take the x outside. And then from here, it's just a matter of isolating for x to get our answer. So in the end, x would end up being log of 400 divided by log of 7, which approximately will be equal to 3.08. So that approach can be used in general to solve exponential equations where a common base is actually not possible on both sides. So we're going to keep that in mind as we look at a few new examples today. As well as we're going to consider an application problem we have not looked at yet at this point. Example 1. So in each case here we're going to solve for x, and we do need to check our answers to make sure we don't have any extraneous roots. And where appropriate, we're going to round approximate answers to 4 decimal places. Now in this particular question, if we examine the left and the right side, we do see a power of 2 on the left, and it is being multiplied by a constant. So in the past, what we've done in this situation is said, okay, let's divide out that constant. So there's just a power of 2 on the left side. So we're going to divide both sides by 4. And that is going to leave us with, on the left, the 2 to the power of 3x. And on the right, well, 60 divided by 4 is 15. Right? The issue now will be 15 is not a power of 2. Which means we're going to have to use the approach we just saw in the introductory example as far as taking the logarithm of both sides. If we do that here, we will have log of 2 to the power of 3x. That would have to equal log of 15. Now on the left side, I can use the power law of logarithms to actually remove the 3x, the exponent, from within the logarithm. So this will become 3x times log of 2. Log of 2 would just be a constant. That would equal log of 15. And now what I would want to do is isolate for x. Now I do realize here that I'm doing 3 times x times log of 2. So if I actually divide both sides by 3 times log of 2, we will end up being able to isolate for x here. X will equal my log of 15 divided by 3 times log of 2. And then once I've actually punched that into my calculator, my approximate answer, and I'm going to go to 4 decimal places here as it's suggested, I should get 1.3023. And we've solved for x. Right, example part B. Now with this one, right off the bat, we can see sort of the issue at hand that, again, we've got a power of 5 on the left, power of 3 on the right. So clearly a common base is not going to be possible here. So what we'll do, same basic approach as the last question, we're going to take the logarithm of both sides to start. So I'd have log of 5 to the power of x minus 2. That would need to equal log of 3 to the power of x plus 5. Now we're going to use the power law here for logarithms to sort of start to simplify, but I do need to realize in this particular case that my exponent isn't just a monomial anymore, it's actually a binomial. So I'm actually going to at least envision brackets around the terms in the exponent because I need to sort of keep them within exponents when I actually use the power law here. So what I'll have is on the left side, picture x minus 2, that being multiplied by log of 5, and that would have to equal x plus 5. So again, I'm using the brackets, and then times log of 3. Right? So again, the brackets are important here just to sort of represent the entire exponent. Right? From here, what we're going to do is actually expand. So picture x log 5 minus 2 log 5. That would have to equal x log 3 plus 5 log 3. Now at this point, the goal is again to solve for x. What I would want to do from here though is collect all of the terms involving x on one side and all of the constant terms on the other. What we could do at this stage, again, the goal is isolating for x. What we should realize now is there's actually a common factor of x on the left side. So whenever there's a common factor, usually it's a good idea to remove that common factor. So we're going to factor on the left. We'll take the x out. So I'd have x times, and then I would have log of 5 minus log of 3 as my leftovers. And then on the right side, there really aren't any common factors there. So I'm just going to leave it as is. At this stage, what I would want to do now, if I wanted to isolate for x, I could divide both sides by the expression that x is being multiplied by on the left, which is log of 5 minus log of 3. Now technically at this stage, we could punch that into our calculator because we've isolated for x. We could determine an answer here. Or what we might want to do, just because that's sort of an awkward calculation to do all at once in our calculator, we could simplify. So there are some options here. So what I'm going to do, I'm going to picture in the numerator here another way of expressing what we have. Now technically, I could actually represent 5 times log of 3 as log of 3 to the power of 5. If I just pictured using the power law, kind of in reverse here. Similarly, 2 times log of 5, that's the same as log of 5 squared. In the denominator, if I sort of do some simplification there, that's a difference of logarithms with the same base. What I could do there is use the quotient law in reverse, which is to actually convert this to log of 5 divided by 3. That's what I'm going to do. Log of 5 divided by 3, that would be equal to the denominator. I'm going to do a little bit more work with the numerator before we actually decide to punch things into our calculator. What I need to realize here is I've got a sum of logarithms on the top, so I could actually convert that to a single logarithm. So this could become log of 3 to the power of 5 times 5 squared. I'm just using product law in reverse, and then I'm dividing by log, again, of 5 over 3. Now what I'm going to do now is picture, well, 3 to the power of 5 times 5 squared, that's to 6,075. So I'm actually going to do a little bit easier calculation now, which is equivalent to what we had before. It's just a little bit easier to actually punch into the calculator. Once I do that, the answer I should end up getting, and again, we're going to 4 decimal places here, I should get 17.0546. Now you could, if you wanted, just for practice on your own, compare and actually try entering into your calculator the value for x at the stage we kind of were at before. So if you wanted to try and verify that you get the same thing, if you punch this into your calculator, that's fine. Okay, last example for today. So this is actually a word problem, and I've decided to actually insert myself into this problem in that it deals with a food that I'm actually a big fan of, and I've always been a fan of, that being Kraft dinner. So what I want to do is I actually want to make a box of this delicious stuff for myself for lunch. And what I would need to do, and hopefully all of you are aware of this as well, because hopefully you share the same love for Kraft dinner as I do, you do need to boil water first. Unless you're cheating and using one of the microwave kinds, in which case you don't. The water coming from the tap, as it turns out for this question, and being added to the pot is actually 5 degrees Celsius to start off with, but increases in temperature exponentially once it is put into the stove. Now, one word to sort of highlight here at this point is the fact that it does say the temperature is increasing exponentially. So that's sort of a clue that this relates to the types of problems we're doing in this particular unit. And then 2 minutes later, the water has actually heated up to 16 degrees Celsius. Now, at this rate, it says, which we actually don't even know the rate yet, that's sort of something we're going to need to determine, how long will it be before the water is boiling? Now, one thing to be aware of in this particular question, you need to be aware that boiling water has a temperature of 100 degrees Celsius, right? So we're trying to figure out, how long is it going to take based on going from 5 degrees Celsius to 16 degrees Celsius in 2 minutes. How long is it going to take to reach 100 degrees Celsius? So the rate, as I mentioned before, we're going to actually have to determine this. Now what we're going to do to sort of set this question up is realize, okay, it is an exponentially increasing relationship. So we're going to try and picture, okay, an exponential relationship in general kind of has a specific look to it. Okay, so an exponential function in general is normally of the form. Now we've looked at different types of exponential relationships, but the basic idea is we start with an initial amount, which is typically denoted as a0, a rate of increase or decrease, which when we did doubling problems, x would have been 2, half-life problems, it would have been 1/2, that kind of thing. And then our exponent, in this case, because we're looking at time, t would make sense for our exponent. So as far as that should lead to a final amount, in this case, which we'll denote as a. Now, a0 and a will represent temperatures in the context of this question. T will be elapsed time in minutes. Now, what we do need to sort of realize is we have some values given to us to start with that will help us to actually determine the growth rate first. So our initial temperature, the water coming out of the tap, was 5 degrees Celsius. We knew that later on, after 2 minutes, the temperature was 16 degrees Celsius. So we can use a final amount, at least at the beginning, at 16 degrees Celsius. And then the elapsed time between when it was 5 degrees Celsius and when it was 16 degrees Celsius was 2 minutes. So these are all known quantities we have to work with. What we can use this information to do is actually figure out a value for x. So if we set up an equation with those values substituted in, we're going to have 16 equals 5 times x to the power of 2. So in order to solve that, picture isolating for x. I'm going to divide both sides by 5. So I have 16 over 5 equaling x squared. To get x at this point, all I would need to do is actually square root both sides. So 16 over 5, if I square root that, I'm going to get x. Normally, when you square root both sides of an equation, there is a positive and a negative solution. We're going to ignore the negative solution here simply because our growth rate needs to be a positive number. So now what we'll do is actually consider, well, we were trying to get to 100 degrees Celsius, so we're going to have to picture, we have a new growth rate to work with, so our model can now be represented in terms of that value of x. So what we'll do from here is basically assume A is 100 degrees, and then we can use, we kind of have the choice. If we're starting from time 0, we used A0 as 5 degrees Celsius originally. So our model actually will be A equals 5 times the square root of 16 over 5 to the power of t. So we're going to set, we could technically set this question up where A0 was 16, but then we have to realize the time we solved for was not accounting for the 2 minutes that elapsed between when it was 5 degrees Celsius initially and 16 degrees Celsius. So you can technically solve this one of two ways. I would recommend just using our original A0 value again here as A0. So now our equation becomes, so this is actually an exponential, this is an exponential equation. We will have to solve for t. It will be very similar to the previous. So what I would do at this point, I do see the 100 on the left side, the 5 multiplying my my base to the power of t on the right. I would divide both sides by 5 at this point just to sort of simplify a little bit. So if I do 100 over 5, that would now have to equal the square root of 16 over 5 bar t. Now 100 over 5 will just reduce to 20. So I've now got 20 equaling the square root of 16 over 5. All of that to the power of t. Now the issue here is going to be we don't have a common base to work with. Now 20 is not a power of the square root of 16 over 5, or at least not one that would jump out at us. So what would make sense to do now is what we were doing in the previous examples to this, which is to actually just take the log of both sides. So what we could do at this point is do that. One other thing we may want to consider, and this would just make solving this a little bit easier. We could have done this earlier, but the square root of 16 over 5, it might be easier to picture that as actually being, might be easier to picture this as 16 over 5 to the power of 1/2. So what we'll do, wouldn't necessarily need to do this, but I think it may make it easier to solve for t if we do that substitution. So picture now, this is actually going to be an equation 20 equals, and now I have 16 over 5 to the power of, well, 1/2 times t, or t over 2. Okay, so now what we'll do is we'll take the logarithm of both sides. So I have log of 20. That would have to equal log of 16 over 5 to the power of t over 2. And now on the right side, I'd be able to use the power law here. So we're going to get log of 20. That would have to equal t over 2 times log of 16 over 5. And then what I would do to both sides at this point is multiply by 2 so I can get rid of the coefficient on the t on the right side. So picture 2 times log of 20. That would have to equal t times log of 16 over 5. And then the last thing I would need to do to isolate for t is divide both sides by log of 16 over 5. And at this point, that would be when I take out the calculator and evaluate what this is going to equal. So in the end, 5.15. And in this case, the time units are in minutes. Okay, so it's going to take me, Mr. Wilden, a total of 5 minutes, 5.15 minutes, or if I wanted to convert that into how many seconds, 0.15 minutes, I could reduce into seconds. So if we wanted to do that, so if I did 0.15 times 60, so what we end up getting is that it would actually take 5 minutes and 9 seconds, approximately, for the water to boil. So that brings us to the end of the lesson for today. If you have any questions, just be sure to ask them in class tomorrow, and have a good evening. Bye for now.